right, so I think we're recording, and Meredith, we're going to do our best today to make sure that you can hear us. Erin is suffering with allergies, and she's a bit hoarse, kind of froggy in the throat, so I don't know how well you'll be able to hear her, and you know, I'm so naturally soft-spoken, you might not be able to hear me either, but we'll do our best. Today, we'll be focusing on binomial probabilities and Bernoulli trials. And so first thing I'm going to talk about is what the requirements are for Bernoulli trials. Bernoulli trials, by the way, are named after Mr. Bernoulli. I think his name was Jacob, and he's a mathematician back in the early 1700s. And so he came up with this idea of probabilities that have only two outcomes, either success or failure, and the idea of doing something repeatedly where the trials are independent of one another. So we could use, you know, for real simple examples, something like rolling a die or flipping a coin or something like that, where the success or failure of any outcome is totally independent of the outcomes that preceded it. So that's what we're looking at, and gosh, our projector is shaking at the moment. Hopefully, Meredith, you won't have to endure that. I don't think the shakiness comes through on your video, but we'll see. I'm sure you'll let us know. So anyway, back to Bernoulli trials. We have a series of independent trials or observations. Only two possible outcomes, either success or failure. So for rolling a die, success might be something like we get a 3, and failure is we get anything other than 3. Or for flipping a coin, success might be that it comes up tails, and failure that it comes up heads. So again, those are simple examples. We'll see some more interesting examples when we get to the opportunities later on. But for now, just an introduction. And then the last qualification for Bernoulli trial is that we've got, you know, this probability of success. If we call that P, then the probability of failure, since there are only two outcomes, probability of failure is 1 minus that. And I think the projector is already getting hot. I'm going to open the window. All right, so I've got some examples here. We talked about rolling a die or flipping a coin. You might think of shooting free throws. You can use your own opinion about whether those events are really independent of one another, because personally, you know, by the time I'm at the 20th free throw, the probability of me hitting it, my arm's getting tired, it's probably close to 0. So 20 free throws would not be independent events for me, but they might be for somebody who plays a lot of basketball, shoots a lot of free throws. Okay, moving right along here. Any questions? So we have a little activity that we'll be doing today. I borrowed this from Texas Instruments. They send out, if you're on their mailing list, they'll send out a list of or periodic activities that can be done. So I'm officially giving them credit for this. And so what we'll be doing here is an example of a Bernoulli trial, or series of Bernoulli trials, rolling a die, and we'll be doing that 5 times, and then recording in this problem, this table number 1, how many successes we have and how many failures we have in 5 rolls. All right, and then as you can see, there are more than 5 lines on here, so we'll actually do this experiment 10 times. So where each one of the experiments consists of rolling the die 5 times. So 50 rolls in all. And each time we'll keep track of how many of the 5 trials were successes and how many were failures, with success being that we roll a 6, and failure being that we roll something other than a 6. All right, so Erin, are you ready to roll, literally? And let's go ahead. Actually, we're going to keep tabs and item number 1, row number 1 will be 5 rolls. Okay, so until we get to 5, we're still in the first row. And you can just keep your, keep your tabs there. There you go. Okay, and then on to the next set of 5. This would be a time when it would be really nice to have one of those smart boards that'll let 2 people do something at once. Oh, good idea. Alright, so no successes in that one. Yep. I'm going to pause this recorder for a minute. Be back in a minute, Meredith. Alright, so for table 2, what we'll do is record the results from table 1. So we're interested in the number of experiments where, let's see, they want trials or experiments. Yeah, I think that should say number of trials instead of number of, it should say number of experiments instead of number of trials. So the number of experiments where we had 0 successes. Well, out of the, let's see, is that right? Let's think about this one. Yeah, that's right. So 0 successes would be this one, oops, this one, this, and this. So there were 4 instances where we got 0 sixes. So 4 out of 10, 24. And then we had 1, 2, 3, 4, 5 times. And we had 2 once. And we had 3 0 times, 4 0 times, and 5 successes 0 times. Does that make sense? Okay. So next thing we're going to do is let the calculator do a simulation for us, and that actually goes quite a bit faster than if we're doing it just rolling one at a time. So there's a calculator command here that will do it, and it's a random binary command. So if you get to that, let's see, let me call the calculator at one from there. And then the arguments are these. 5 is going to be the number of trials in each experiment, and 1/6 is the probability of success, and 10 is the number of experiments. So we're basically recreating the experiment that we did over here in problem 1, but we're doing it using a calculator. And then the calculator will have as output down here the total number of successes in each one of the experiments. Alright, so random binary, 5, 1/6, then 10, and I think it's under probability. Yeah, so on option 7, 5, comma, 1, 6, 10. And then your output probably is different than mine because it's a random experiment. So mine randomly came out with these numbers of successes, and yours probably looks different from that. All right, so on your paper you can fill in chart 3 what you got, and then I'll fill in for what I have up here. So let's see what we got. Actually, I think you can also store this under in a list in the calculator, so I'm going to do that. I think it's easier to summarize. So I'll store this, and I'm putting it in this one. And then if I go into the stat menu, I can sort list 1, sort that in ascending order. And now when I go in and look at it in the stat menu, it's really easy to summarize. So in my case here, I have 2 experiments that had 0 successes, and then 1, 2, 3, 4, 5. 6, 1. What were your percentages, just for comparison?
I had 0.3 under 0, 0.5 under 1, 0.2 under 2, and then 0 in the rest.
Okay. And so your outcomes were, the results were sort of a hybrid between this table 3 and table 2 on that. All right. What do you think would happen if instead of running, let's say instead of doing 10 here, so 50 trials altogether, let's say you did 100 experiments instead of 10. What do you think would happen over here in the results?
It could be closer, like we have more in order to.
Okay.
Anything else?
Okay. And we still do. We do have that here. But like I probably wouldn't be seeing this in the 3 column. I probably would be seeing 2 of those. That's actually going to be fairly rare. So both of these, even though we did one with the calculator and one by rolling the die on the smartboard, they're both still experimental probabilities. And so what we'll look at next are the theoretical probabilities associated with binomial probabilities in vanilla trials. All right, so when I switch this page, we're actually skipping a page on the first section of that document because I didn't like the order in which they did it. They actually went straight to using the calculator to do the theoretical probability, and I wanted to develop that formula first. So that's why things look a little different here. I've got things out of order. So we have an example here of some outcomes, and we could imagine that this experiment that we're doing might be rolling a die again, or flipping a coin, or free throws, or something. But it's a binomial probability. So binomial, of course, means 2 names, or in this case, 2 outcomes. So success would represent a positive outcome, and failure a negative outcome. And so here's one possibility for how we could get 2 successes in 5 trials. Okay, does that make sense? So we roll the die 5 times, and maybe it is the outcome of the successes getting a 6. And we have success, failure, failure, failure is one of the possibilities. we will, we got 2 6s in a row, and then we got 3 of something else in a row. So this first question then, number 7, says, list all the arrangements of 2 successes and 3 failures. So what are some other ways that we could list outcomes, 5 outcomes where we've got 2 successes and 3 failures?
Success, failure, success, failure, failure.
Okay. Okay.
Success, failure, failure, success, failure.
Okay.
Success, failure, 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 success.
All right. So we've covered all the we have covered all the possibilities now where we have a success in the first spot and 1 success somewhere else. Okay. What else?
Failure, success, 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 failure, failure.
Okay.
Failure, success, failure, success, failure.
All right.
Failure, success, failure, failure, success.
All right. So now we've covered all the possibilities where we have a success in the second spot and somewhere else. Okay. What else?
Failure, failure, success, success, failure.
Okay.
Failure, failure, success, failure, success.
Yes. Now we've covered all the possibilities where we have a success in the third spot and somewhere else.
And failure, 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 success, success.
All right. Does that cover it? How many have we done all together?
10.
Okay. And what might have been a way that we could have predicted in the beginning that we would have 10 outcomes here using one of our nifty counting techniques?
I choose 2.
5 choose 2. Very good. So we've got 5 slots because of the 5 trials. And out of those 5 slots, there are 2 ways of picking a position for a success. Because we want to know the number of different ways that we can have 2 successes. So yeah, 5 choose 2 would have given us that to start. 5 choose 2. That is equal to 10. All right. So with that in mind, now let's look at what the probability is of each one of these arrangements. And just to keep things simple, we will go back and assume we're still dealing with that first experiment that we did, where we're rolling an eye, and 6 is a success, and anything else is a failure. All right, so what's the probability of this first outcome here? It says F, F, F. Probability? Okay, what's the probability of getting a success just on the first roll? Okay. And then probability of a success on the second roll? And what are we going to do with these 2 numbers? If we just wanted to calculate a success on the first 2 rolls. Multiply, and how do we know to do that?
You want this and that.
Okay. And it indicates the multiply, and also we know we have this new term now, relatively new, independent events, and so if the events are independent of one another, we can get the probability of them happening by multiplying the 2. So yeah, multiply them. What about probability of a failure?
5, 6.
Okay. And then another failure. And another failure. So this represents the probability of that first outcome. Success, success, failure, failure, failure. What is that probability?
I got 125 over 7,776.
76. And what is that as a decimal?
0.016.
So about a 1% chance of getting 2 successes and then 3 failures. What if we looked at one of the other outcomes here? So suppose instead of this one, we want to calculate the probability of, I don't know, how about this one right here? What's that probability?
Be the same.
Okay, yeah, because even though things would appear in different order, like we had 5, 6 times 1, 6 times 5, 6 times 1, 6 times 5, 6, the product would still be the same. The product of the numerators, product of the denominators, and so we'd still get the same probability of 0.016. All right. Again, we had 10 of these outcomes. Each one has a probability of 0.016 of occurring. So how do we find the total probability of getting 2 successes and 3 failures?
You multiply 0.016 by 10.
Okay, and so we're going to get 5 choose 2 times 0.016, or 10 times 0.016, which is 0.16. What is 0.16 as a decimal?
4/25.
I mean, as a fraction, 4/25, okay, which is close to what?
Close to 1/5.
It's, yeah, between 4/25. 1/5 would be 5/25. And if we went down to, you know, well, so we know that it's a little bit less than a 1/5 probability. It's not down to 1/6. 1/6 is what written as a as a fraction.
I'm sorry, I didn't hear the question.
That's because it was a dumb question. That's why that didn't make sense. Suppose we wanted to. What is 1/6 as a decimal? Is what I meant to say.
It's 0.16667.
Okay, so this is a little bit less than that. Just plain 0.16. Or let's see, was this rounded off or did this come out just 0.016?
It was like 0.01607.
Okay, so this is, our probability is going to be a little bit less than 1/6. Actually, okay, yeah, that's right. Now, if we go back and look at the previous page here, which I think that's going to cause problems because I'm going to have this writing all over it. No, it's okay, good. That's actually how I wanted to look. If we look at the probability of exactly 2 successes, we came out with a 0.1 probability up here in the empirical or the experimental probability that we did by rolling the die, and down here in the second table, excuse me, table 3, I got 0. What did you get for your probability there?
I got 0.2.
Okay, so neither one of us was dead on with the theoretical probability. Suppose we did this again, and we talked about this a second ago. What happened if we looked at 100 trials here, down here, instead of just 10 trials? Do you think it would be closer or farther away from the experimental, from the theoretical probability?
Closer.
Yeah, it should be. The more trials we do, the closer it should get. All right, so let's go ahead and run that on the calculator. So let's do the random binary, 5,16, and let's make it 100. Got to think about it for a minute. Data type. Okay, let's run it now. you have an error on yours? No? Okay. What did I do? 5, comma, 1, 6, 100. Okay, I guess that mystery is solved. So we could, again, put this into a list. So I'll store it, put it in list 1. And then we can sort list 1 by going into stat. Option 2, list 1. And we should be able to put that, let's see, but I don't know if we'll just do a histogram for that or not. Maybe. So plot for list 1. Make sure that plot is on and it's on histogram. And the window's probably going to be all messed up, but let's see here. 0, 7, actually that looks pretty good. Trace it. So I've got 47 zeros in there. And 37 ones. Fours, fives, or sixes. Wow. That's a little bit surprising to me. How'd your results come out?
The last one I did the Instagram.
What's that?
You asked me on how you made it.
Oh, sorry. Okay, so did you store your results in list 1? And then if you don't really have to sort them. I did that just to kind of get a visual, but actually it might not happen when there's 100 numbers, so it's better just to put it in the histogram. So second, stat plot, and when enter, make sure your stat plot's turned on. And then for the type, you want to be over here on this one, which is a histogram. And then your X list is list 1. The frequency, I don't know, I'm not sure what that actually represents. We're going to just leave it alone. And then let's go ahead and press graph. And then you might need to reset your window, depending on what your window is set on now. My X min is 0. X max is 7. Really, it wouldn't even have to go that high, but this works. And then X scale is 1. You want your bars to be 1 unit wide. And then Y min 0, Y max up to 100, because technically you could have, up to 100 outcomes in one bin, although it's highly, highly unlikely. And then just press graph.
Um, 53 zeros.
switch this over. Okay, so that's fairly close to what my outcome was.
36 ones,
Okay,
8 twos, and 3 threes.
all right, and that one was dead on. So these, your numbers and mine, when we ran 100 trials, were, actually, I guess I should have put that down here, but I don't have room. But with 100 trials, our numbers were fairly close. And so what we'll do now is go back and look at the actual probabilities, the theoretical probabilities for each one of these outcomes. All right, so we've got our sort of a formula that we arrived at over here. We said if we take 5 choose 2, you know, if we're looking for 2 successes, 5 choose 2 times 1 6 times 1 6 times 5 6 times 5 6 times 5 6. So we'll repeat that sort of thinking for each one of the other outcomes. All right, so if we wanted to know the probability of 0 successes, then instead of just 5 choose 2, it's going to be 5 choose 0 here. So 5 choose 0. 5 choose 0 times 1 6. We don't have any factors of 1 6 because we want 0 successes. So we're going to have 5 6 times 5 6 times 5 6 times 5 6 times 5 6, all failures. So 5 6 for the fifth. And of course 5 choose 0 is 1. What's your?
I got 0.418 or 0.419.
All right, so that's the theoretical probability of having 0 successes.
0.4019.
That's
My bad.
okay. 0.4019, and now let's come back and whoops, I'm on the wrong page. And I've got 0.47 for my theoretical probability, my experimental probability, and you had, was it 5.3?
5.3.
Okay, so that's fairly close, certainly closer than the 0.4 that I started with. So you can see it's getting closer to the theoretical probability of point, oh wait a minute, no it's not. That's not, we got farther away. Okay. Oh man. That's not the way it's supposed to go. Okay, well, it is what it is, you know. Maybe if we tried it 1,000 times, or at least 200 or 300, you'd get closer. Goodness. Okay. So all my mathematical theory out the window for the day. All right, let's try it with 1 success and see how we do. That's embarrassing. All right, Meredith, if you're laughing at us, we're going to haunt your dreams. All right, 5 choose 1 times 1 6 to the first times 5 6 to the fourth. Does that make sense where that came from?
I got 0.335.
335. All right, let's see how we did with this one. Dare I even look? 335. Okay, this one did much better. For me anyway, and I think yours was close to 0.37, wasn't it? Yeah, so definitely going from 0.5 down to 0.37 or right around there is moving in the right direction. So in spite of the fact that the first one didn't go quite so well for us, second one we're dead on here. All right, what about the probability of 2 successes? Oh, we did that already. 3 successes?
I got 0.032.
What was it?
0.032.
All right, so about 3%. Let's see how we did. Amazing. What was yours?
Same.
All right, yay, finally we're going in the right direction. And I'm guessing these two guys over here are going to be very close to zeros, but we'll see. So 5 choose 4. And then 6, 4 times 5, 6 first.
And 0.0032.
Okay, so yes, it is quite close to 0. And then the last one, choose 5, which of course is 1 times 1 6 to the 5th. And just the fact that we've got 6 times 6 times 6 times 6 times 6, did I get 5 of those in the denominator, tells us it's going to be a very small number.
And at 1.29 times 10 to the negative 4.
Okay, so that is extremely small, and that's what we would expect, and our experimental probability bears that out. Okay, does that make sense? All except for this one up here. It's not that far off, it's just, I would like to have seen it going the right direction, and it didn't, but that's how these things work out sometimes. That's why it's called an experiment. All right, let's see, we've covered 8, and 9, and 10, and we haven't actually formalized this theorem or this formula in number 11, so maybe we should do that now. So I'd like to go back and erase, actually I'm going to erase most of this. That's okay, or even if it's not. So here are the formula for finding a binomial probability. I want to make it look like what your book did, and so we're going to let n equal the number of trials, total number of trials. In the example that we just did, it was 5, because we were doing 5 at a time. But n is total number of trials. K is the number of successes. P equals the probability of success. And Q is the probability of failure. And we know, of course, that Q is equal to 1 minus P, because P and Q are the only possible, we only have 2 possible outcomes. So the probability of one of those is P, and the probability of the other is 1 minus P. So Q is equal to 1 minus P. All right, so let's go back to the method that we were just using and see if we could state, using these variables, what that formula should be. We want to know the probability of K successes. So like we just did, the probability of getting 0 successes in 5 rolls of the die. And probability of getting 1 success, and 2, and so on and so on. Let's generalize it. Probability of K successes. So how will we do it?
We start with n choose K.
Exactly, let's start precisely with n choose K, you're right. So n choose K. And then what?
P to the K.
Very good. Probability of success on any one trial raised to the number of successes we want.
And then Q to the 1 minus K.
You're really, really, really close.
N minus K.
Yeah, n minus K. Good. So number of trials minus the number of successes. That gives us the number of failures. So this is exactly the formula for finding the probability of K successes in n trials and Bernoulli trials, where P is the probability of success and Q is the probability of failure. you'll see that formula in your textbook. Now you know how to derive it on your own. That's very good. All right, so, we could go back and do this question. It's kind of trivial at this point. I don't think we really need to really repeat that. But I am interested in looking at, the second part of this question. So we've got some multiple choice test where the probability of guessing a correct answer, hopefully you don't have to guess that much on every single question, but we'll go with what we've got here. So probability of randomly guessing a correct answer is 0.25. And there are 15 questions on the test, and we're assuming that it's independent. Whether you get one correct doesn't have any bearing on whether you get the others correct. So these are independent events, and we want to find the probability of not exactly 10 answers, but at least 10 answers correct. At least 10 correct. So what would be a good way to do that? Or what would be one way to do that?
You find the probability of getting 10 answers right, and then add it to the probability of getting 11 answers correct, and all the way up to 15.
Right, exactly. Which would be kind of a pain to have to go through 6 calculations and then add them all together to get this result. So it turns out there is a better way, and the calculator provides that for us. So let's go back to, I'm going to the next page, but you're actually looking at the previous page. So your calculator has a couple of really nice features for doing binomial probabilities. It will actually do the calculation that we just did, the formula that we just developed. It'll do that calculation for you. It'll also find binomial probabilities for, well, let's repeat it. It'll do what we just did. So we could fill out this chart pretty quickly by going in and doing this binomial PDF function where we're doing 5 trials and probability of success 1/6, and it'll give us the whole distribution for every single one of these. Probability 0, 1, 2, 3, 4, 5. And so let's do that. And on your calculator, you get to it by going to the second distribution option. So let's go into this. And go to the second VARIS, which is this VISTR button. And I think it's option 0. Option A, binomial PDF. We'll talk about that binomial CDF in just a minute. The binomial PDF is probability distribution function. So let's go to that. And then the arguments are, once again, the number of trials and the probability of success on each trial. Let's get back over here. So 5, comma, 1/6. Enter. And we should be able to check the probabilities that we did using the manual development of the formula with this. So the first one, I might be able to store this on the list. Maybe that's a little easier. Let's go and store the next one. And then we'll look at this one. All right, so 0.40188. Notice that the probability of 0 successes and 1 success are awfully close to one another. I don't remember us getting that. Did we get that? 0 and 1 coming out the same. Okay, something went awry here. I wonder if it's a round off thing. 6. Oh. Okay. Let's see, we've got a problem here. These numbers in green, these were the ones we got when we did the calculations, or were these the ones that they now I've forgotten whether they were the ones the calculator did for us.
Which one you got on your, you did
That was for 100 trials. Yeah, okay. Where did I record our actual probabilities? That's what I don't remember.
Just like talk about it.
Okay. Okay, so you can enter the formula on your calculator that we were using, the one that we developed, and you'll see where these answers came from over here. So like if I did, if I want the probability of 0 successes, I could do 5 choose 0, which is 1, times 1 6 2 0, which is 1, times 5 6 to the 5th, which is 0.4018. So that's where this came from. All right. We'll continue this tomorrow, and we'll go over homework tomorrow. I suspect it may take a little while to go through that homework. Mine came out to be 8 pages, I think, when I did it over the weekend, so it's a bit lengthy. So that'll take a while. But we'll finish going over this tomorrow, and we'll work on homework. And Meredith will be back. Meredith, I'm going to post this on YouTube. I hope you'll run out of patience with it. It's about 45 minutes, but it is engaging. I mean, you got to admit, it's probably the most fascinating thing you've seen in, I don't know, hours.